All right, so let's see, I think this, you can see this board. A lot of classroom spaces are taken right now, so I'm gonna be working on a little board. And hopefully, we can still see everything clearly. All right, so I've always given my classes some values to memorize, e to the different exponential values, e being 2.71 if you're just coming in. And without any background on e to the x. So I just took them off the calculator. If I want to know what exponent I put on top of e to get 7. Well, then I gotta push the button ln(7). It's a logarithm. It's got its own notation system. And the ln(7) will tell me what the exponent is on top of 2.71 that gets me a 7. All right. So there are these things called logarithmic rules, and I think we can organically develop them by practicing skills like the ln(6), knowing that we have some approximations. E to the 0 is exactly 1, but e to the 0.7 is 2, and the reciprocal of 2 is 1/2, and that we've been studying negative exponent. So if you know e to the 1.1 is 3, then you know that e to the negative 1.1 is 1/3. I generally don't work with e to the negative 1.6, but I'm getting tired of working with just 2s and 3s. So I thought I'd throw a 5 in there. And so I'm asking you now to memorize that negative 1.6 is the exponent you put on top of e to get approximately the value 1/5. All right, now, if you memorize these, then there's no excuse on the next test for not plotting e to the x. A lot of you are still leaving it blank. Done it every test now for weeks, which means you're not looking at it. So let's take a quick look at it. The values that I asked you to memorize are here. All right, I think I can stand off screen and say that, well, negative 1.6, I've just gone from negative 2 to 2 and done some estimating. I figure that's about halfway, so negative 1.6 is a fifth. I've used the marker for 1 unit. I think I did it with one of these ways. Just shorthand here, just got 5 units of change. And so negative 1.1, 1/3, I said that's about a third of the way up to 1. Negative 0.7 1/2, 0.7 to the left of a half, so I called that. That looks like it's a little high. Halfway up would be here. Okay, so it's a little higher. And all I'm doing is plotting these values. 1.6 getting me 5, and geez, I think we can see connecting the dots almost gives us the curve. I hope you can probably, understand that it's going to positive infinity on this side and heading to 0 on that side. That's asymptotic behavior over here. So that's not the purpose of this video, but I thought I would say that because there's no reason not to be able to graph e to the x if you simply have a little number sense. All right, so ln(6) is asking the question, e to the what gets us 6, and we have some values here that help us get the number 6. 6 is 2 times 3, that's 6, and 2 is e to the 0.7 times 3 e to the 1.1, and at this stage you should know your rules of exponents that you add 0.7 plus 1.1. So what is ln(6)? It's approximately 1.8. It's the sum. All right, so there's your rules of logarithms. So your rules of logarithms right now are 0.7 plus 1.1 gets us 1.8. And 0.7 is the ln(2). 1.1 is the ln(3). We said on a calculator that's going to get us 1.8, which happens to be the ln(6). I'm seeing a pattern here. Hope you're seeing a pattern. Hope you're seeing the ln of A plus the ln of B is equal to the ln of AB. And we're going to be working with these rules at some point as shortcuts to some of the organic development of them. All right, so I'll give you some practice, organic practice, and then we'll, at the very end of the video, talk about the other 2 rules of logarithms. But you already got one in front of you, so the seed has been planted. How about we do the ln of 10? What is it approximately? You stop the video, you try it, I'm just gonna keep going. Well, I know that 10 is 2 times 5, and I'm doing this one because I got a new number to play with, 1.6. So now I know what 10 is. 10 is equal to e to the 0.7 times e to, I already showed that, so it's the sum, right? And 0.7 plus 1.6, I believe, is 2.3. Yeah, nice. 0.7 gets you, e to the 0.7 gets you a little bit bigger than 2. E to the 1.6 just a little bit smaller than 5. I'm guessing e to the 2.3 is probably just a little bit bigger than 10. But I gotta go to the computer and type into Google ln of 10 just see how close I am to get some number sense. All right, so now let's up the level of difficulty a little bit and you try these. How about we do ln of 2/15? All right, so you're gonna try that. I'm just gonna have some fun with it. I know 2 is e to the 0.7. I know 15 is 3 times 5, so e to the 1.1 times e to the 1, my new friend, e to the 1.6. And so I now know I have e to the 0.7 over e to the 2.7. Oh, that's helpful. So that means it's e to the -2 is approximately 2/15. Because you're doing what? You're doing 7 minus 2.7. So what would the rules of logarithms be here? If you could, we'll call that A, 3B, C5. Well, it's the ln of A minus the parentheses ln of 3 plus the ln of 5. Yeah, so if this is the first time you're seeing it, yeah, something new is hitting the old brain, which means like everything else we're studying might take some time, reflection, repetitive practice, a number of days. Will I give you a number of days? Sure will. You'll get one of these until May 15th. That ought to give you time to sort it out before, we give you a final grade. All right, so that's what we did, really. You added these, right? What is the ln of 3? That was the 1.1. What was the ln of 5? The 1.6. The exponent you put on top of 2.71 to get 5. Right? You added those and you took them away from the ln of 2, which is 0.7. So I hope you can see that, I guess, here most easily. All right, so let me talk about our goals. I should have talked about them at the beginning. So getting familiar with e to the x, that's this graph over here, all right? Let's push this over just a little bit. Marker, got to get that off the desk. All right. And got to be familiar with that. Got to be familiar with some of these values. All right, and now we're looking at rules of logarithms to garner a deeper understanding of this whole process. I might just throw another seed your way. These negative numbers allow us to write a function like 1/3 to the x as e to the -1.1x. If I wanted the doubling function, 2 to the x, then it's approximately e to the 0.7x. So we're getting a universal language, same base for all growth and decay functions. They can be written in e notation. We're going to develop that concept. We're going to work with it. All right, but now back to the task at hand. I'll give you another one. You can try it. How about the ln of 125? What's the exponent you put on top of e to get 125? Well, I think 125 is 5 to the 3. And I think the number 5 can be written as the ln of e to the 1.6. And that is being cubed. And I'm going to put that in brackets. Because this notation looks for the exponential activity on top of e. We don't write the e here. That's what it's asking. Right? I think I can see the exponential activity. I think it's 3 times 1.6. which is approximately 4.8. Okay, so 2.71 to the 4.8 gets me close to 125. All right, now let's develop the rules of logarithms. What do we have here? We have 1.6, which is the ln of, let's call it C. Ln of C, quantity C, and we're multiplying it by 3. And where did that come from? It came from the ln of C cubed. So there was an exponent hiding here, right, above the 5, and where it was actually a 1, right, 5 to the 1. So there's a multiplication here. I don't like the way I said that, but let's see if I can do it with something that's non-base E so you can see it more clearly. Log base 2 of 8, you figure out if that's the same thing as 3 times log base 2 of 2. Take a moment and reflect on that. I hope you say yes. I hope you know that 3 is the exponent you put on top of 2 to get 8. And what's the exponent you put on top of 2 to get 2? Well, 1. And 3 times 1 is 3. So it might be easier to see some of the rules of logarithms there. So we now have another rule of logarithm. We have the ln of a to the b. Let's make it, let's leave it capital B. The ln of a to the b, I'll put it in brackets, is the same thing as b times the ln of a. And I think we're proving it up, or at least seeing it more clearly there. All right, and we'll put all 3 rules of logarithms on the board at some point. So this is not just 5 practices. All right, there's a little lecture going on here. And then we'll practice this skill in another video. All right, so what's the last rule about the ln of 4 25ths? All right, so you pause the video and see if you can get that exponent approximated. And I'll just work with 4 over 25. So 4 could have been written as 2 squared, 25 as 5 squared. I can write the number 2 as e to the 0.7, and that is being squared. And I could have written 5 as e to the 1.6. That is being squared. And I think that's the ln of e to the 1.4 over e to the, boy, brain's getting slow already, 3.2. And that's equal to ln of e to the 1.4 minus 3.2. Our rules of logarithms are there because logs are the exponents. And this is what eventually happened. Did a little subtraction. So I could write this as the ln of 4 minus the ln of 25. That's exactly what this is. E to the 1.4, the ln of 4, e to the 3.2 gets us close to 25. So division becomes subtraction. That's a rule. So therefore, the ln of a over b is equal to the ln of a minus the ln of b. Reaching for that. It's a rule of logarithms. All right, so now I'll show you where you might actually use one of the rules in solving a little algebraic equation. And you can pause the video and see if you can put all the skills together to be able to solve the following. Famous algebra 2. Log base 2 of x plus log base 2 of x minus 2 equals 3. All right, so let's see if you can pause the video. I'll just keep working. And then we will do some part 2 after the lecture. Maybe I got time to do 5 or 6 of those quickly. All right, let's clean the board off. All right, so what do I know? Addition is multiplication of the quantity. So I can write this as a single log. Log base 2 of 2 of x squared minus 2x equals 3. The inverse of log is exponentiating with the base. This is an exponent. This is a base. Where do exponents go? Top of the base. So if I want to get rid of that expression, then x squared minus 2x is equal to the base of 2 with the exponent of 3 on top of it. All right, we now go to algebra 1. X squared minus 2x equals 8. This is usually, taught in the first year algebra class. You set quadratics, you always set them to 0 because you're hoping that you might be able to write this as a product. And you can write it as a product. X minus 4, x plus 2 equals 0. Okay, we can see our answers are x equals 4 and negative 2. Unfortunately, negative 2 won't work because logarithms are quantities in the parentheses. And if you're talking about growth and decay models, you got to have something there. Bacteria, population, radioactivity. You can't have a negative amount of bacteria and watch it grow. All right, so the argument of a logarithm, whatever's in here, whatever that is, it's got to be bigger than 0. Okay, and that's not. So let's look at the number 4 and let's see if it actually works. Log base 2 of 4 plus log base 2 of 4 minus 2, which is 2 equals 3, which happens to be log base 2 of 8. Well, that's a 2. Let's get this out of here. That's a 2. That's a 1. That's a 3. Looks like the rules of logarithms can come into play. All right, so there's a bit of a lecture. I had intended to have it be a skill set, but I think we have to talk about it a little bit, and I'll post it, and maybe you can look at it even before our class when we talk about it in more detail. Get the conversation started. All right, see you in class.